Alright, so now that we covered an example problem in the last thing about how we can relate forces, or relate work and energy, we're going to introduce a couple new concepts with work and energy. So, first thing to introduce is something called the WorkEnergy Theorem, or the work-kinetic energy theorem. This theorem is really simple. It just says, if all my work is done into moving the object, let's say I have work that's done on an object, remember work is a scalar, not a vector, so there's no arrows on it. Some work that goes into the object, and it's only going into making the object move. I don't change potential energy, hence like only change kinetic energy. Well, then I would just say my work is just equal to my change in kinetic energy. Yeah, that's it. My change in kinetic energy is my change in work, I guess. This is really easy. You just say, very easy to grasp a hold of this concept. Yeah, so it seems really trivial, but let's go over a problem that might use this kind of thing. Let's say that we know that we apply some sort of force F of A for a distance x on an object. That's facts. And then we know we can calculate work by doing F of A times x, right? And then let's say we wanted to find the velocity of the object, the final velocity. Well, we just set this equal to EK, which is equal to 1/2 mv squared. We rearrange and we can solve. We get V is equal to F of Ax over m, 2 F of Ax over m square root. Just by rearranging, yeah. So that's the gist of how you would use this theorem. Okay. Next thing we want to cover is something called conservative forces. Dang, conservatives taking our... I don't know. I tried to make a joke. This isn't working. Conservative forces have nothing to do with political party. It's a conservative force because energy is conserved no matter what path you take. What? That's kind of confusing. So let's just take a step back and give an example of a marker. I find a marker at a point A, and I decided to move it to a point B, right? No matter the path I take, right? As long as I move to that point B, the amount of force work I do against gravity is going to be the same, because my final potential energy is mgh, and I started with a potential energy of 0, or let's say, yeah, the potential energy was 0. Yeah, no matter what path I take, I end up with the same energy. And so I would say that Fw is a conservative force, because when the amount of work it does is not dependent on path. Same thing with a spring, right? If I were to compress the spring and then uncompress and compress and compress, and then suddenly compress to a certain point, it'd just be the same as me compressing the spring to that point. Without all the hassle, we still end up with the same energy change, which is Kx, or which is Us. So our spring resistive force, Fr of a spring, is going to be, I did not mean to draw that. Our spring resistive force is also a conservative force. AP test, most likely, is only going to cover these two. The AP test loves these two conservative forces. Yeah, so let's just think about what conservative forces even mean. Conservative forces aren't independent on their path, but what the real important part of conservative forces is the fact that they are always going to decrease our potential energy. If I had some ball, if I have my marker up here, right? I have my marker up here, and I drop it. What's acting on it? Wait, it's a conservative force. What does that mean? Well, that means my potential energy is going to decrease. Did it decrease? Yes, we saw my potential energy decrease, my gravitational potential. Just like a spring, if I were to push it on the board, right, I have some sort of resistive force acting on me, I have some spring potential energy. As soon as I let go, it bounces back to equilibrium. I lost all that energy because this stupid resistive force, darn resistive force, is acting against me. This restoring force. It's a conservative force because it's decreasing our potential energy. So what's an example of a non-conservative force then? Well, a non-conservative force would be something like our resistive forces, right? I made a mistake when I called this a resistive force. This is a restoring force. It's trying to restore the spring. Resistive forces are like air resistance or friction, right? How much friction is acting against me if I move from here to here? Some friction, right? But if I move it, my marker, this whole path, friction is acting on me longer. More energy is lost from friction, right? I'm acting against friction the longer I go. And friction only acts when I move. So if I move a longer path, I have more frictional force that's acting against me. Friction is not a conserved force. Same with air resistance. If I moved it this way, I'm going to have a different air resistance then, or a different amount of work that's done by air resistance if I move it around in circles and things like that. Alright. Cool. So now, let's talk about the final thing for this video, which is going to be how change in potential energy and the work-kinetic energy theorem relates. So, now that we've talked about conservative forces, let's imagine we start off with some amount of potential energy. Like, let's say I have a track and it goes wheel. If I have a track here, I start off with some sort of potential energy. Okay, if my potential energy somehow increases, right? Then, or sorry, let's first consider that I went down here, right? That means my potential energy decreased, right? I have U goes down, U goes down, E goes up, EK goes up. But if I increase my potential energy, right, U goes up back to here, my kinetic energy is going to decrease. So that's something important to know. Potential energy goes down, kinetic goes up. Potential goes up, kinetic goes down. That's because conservation of energy. So if I have, if I want to find how much work my kinetic or my conservative force is doing, right? Conservative forces are always going to decrease potential energy. So that means my kinetic is going to rise. So if I say I have my potential energy, I have some sort of change in potential energy, is going to be some function of my conservative force times x, right? Maybe it's positive, it could be positive, it's negative, I don't know yet. Now, let's think. If my force is acting on it, right, so positive force in the same direction, positive direction, right, so like my force is acting this way, my direction, the box is moving down, right, acting in the same direction, force is in the same way, then my potential energy decreased. So, I have to say my potential energy change is going to be the negative of the work done by my my conservative force. Same here, right? If my force is this way, the box is moving this way, but my force is this way. So F and X are negatives of each other, so I end up with Fc times, or absolute value of Fc times absolute value of X. This is going to be positive because a negative, one of these is negative, times a positive times negative again is positive. So I get positive change in gravitational potential. Awesome. Yeah, so that's cool and all, but what else can we do with this? Well, we can consider things called equilibrium states. There are two kinds of equilibrium. Equilibrium just means, remember, like the spring, it stops moving. There's not going to be any motion. There are three types of equilibrium. First, there's a stable equilibrium. First things first, only occur when my force is zero, right? And we know when we plot our our energy versus our distance. If force is zero, right, we know F is equal to U du dx plus or minus. I don't really care right now. Okay, fine. Minus du over dx, right? So it's the slope of this line, slope of this curve, right? It's going to be 0 here, it's going to be 0 here, right? It's going to be 0 here because it's just a straight line. So it's going to be 0 wherever it's a horizontal, wherever I can draw a horizontal slope. I'll keep that up here. Alright, so there's three types of equilibrium. First, we have stable equilibrium. Imagine that we had a bowl. Right? Imagine that this is a track. Can this be a track? Yes, of course this curve can be a track. Right? It's as if we're saying, as we move along this track, a certain distance to the right on this track, right, x distance, my potential energy is decreasing, right? Potential energy, that could just be our gravitational potential. I don't care. Let's just think of it as gravitational potential energy. Let's think of this as a track. and potential energy decreases here. If I were to drop a marble, if I were to drop a marble anywhere from, if I were to drop a marble anywhere near this place, or any point near here, it's always going to roll down to here. So this is called a stable equilibrium. Because any point near this equilibrium is going to go to the same point. It's going to become stable and it's going to be the same point. It's just like a spring. If I uncompress a little bit, it's going to wave a bit, but it's always going to end up in the equilibrium position. Unstable equilibrium, on the other hand, right, means that anywhere near the equilibrium, it's going to roll in some direction. It's going to roll away from the equilibrium. If it's to the right of it, it's going to roll to the right. If it's to the left, it's going to roll to the left. But if it's right at the equilibrium, it's going to stay exactly still. That's just like balancing a pencil. If it's right on the tip, if you get it perfectly, which is like near impossible, then it's going to stay still. But if it tips in any direction, if we started it tipped in any direction, it's going to start rolling. Finally, neutral equilibrium is just a straight line. It's just like right here. A straight line, no matter where I put it, it's going to stay still, near the equilibrium. Alright. So those are the types of equilibrium. Yeah, so those are cool terms to consider that the College Board might throw at you. My underlying tip for this video: imagine the potential energy versus, if they give you a potential energy versus distance graph, just imagine it like a track. So you can think about how much potential energy there is, you can think about how much kinetic energy there might be. Just think of it as a track, because we know how to do tracks. We just did a practice problem on that, right? Alright, this is, yeah, let's go study. Yay!